Okay, awesome. Hi, Dineke, how are you?
I'm doing very well. Thank you for asking, Mark. So how are
Thank,
you?
good, thanks. Thank you for the opportunity for us to learn from what you're doing over there in the Netherlands. Um, Maybe we can start this off with a brief introduction. You can tell us who you are and what you do and how you got started.
Yeah, sure. So my name is Dineke Verbeek, and I'm an associate professor at the University of Groningen. And as an associate professor, I'm mainly involved in research, but I also do quite a lot of teaching at the medical faculty. Yeah, majority of people, when they search for me in PubMed, so this is the scientific library, they will find out that most of my research over the past decade has been focused on spinocerebellar ataxias, and with a highlight on the genetic component of the disease. And this is actually where it all started, and how I got into contact with this disease, with spinocerebellar ataxia, was during my second internship during my master's program at the University of Utrecht. And that was already back in 2001. So this is actually how it all got started. And now we, over the last 10 years, we have continued to expand our research lines on different types of spinocerebellar ataxia, types that we have discovered ourselves as a team. So the genetic components, we discovered those. We actually expanded to further investigate the disease mechanisms in all kinds of model systems in our laboratory to better understand how this disease affects the cerebellum. And we just want to learn from all the experiments that we do with, of course, the endpoint is that we want to intervene or try to stop this disease from progressing or even from occurring. But this is a step that is still far away. But we're taking small steps over the last few years. But I think we're getting in the right direction. Yeah.
Was there something that caused you to choose spinocerebellar ataxia research or study?
Yeah, this is a very interesting question. So I think the encounter with the disease was just, I didn't choose to work on spinocerebellar ataxia. During my master's programs, I was highly fascinated by human genetics and that, how small changes in our DNA that sometimes they would just be benign, but on other places in our DNA, they would cause disease. And I had this fantastic course, genetic course, and there was this great teacher, and he was extremely enthusiastic. And at that time, I thought I need to get in touch with this professor and ask whether or not it would be possible to do an internship in his or her in his laboratory. And this professor was happy to have me as a master's student at that time. And then he proposed to work on a project related to the genetics of an unknown variant of spinocerebellar ataxia. And my task was to map the disease gene, this new SCA gene in this family, using the very traditional genetic methods that we still were using at that time. So I didn't really make the choice myself. This was just a project that was offered to me. But it was so close to what I enjoyed and where I thought that I could really bring something to the table that in all the years that followed after my graduation and even during my PhD, the disease, I never let go. It was always one of my major focuses.
Yeah. Now, for the people that are newly diagnosed, or maybe they don't know anything about SCA, do you want to describe what it is?
Yes, so spinocerebellar ataxia is a dominant disease that has many subtypes. So it's genetically very heterogeneous. This is how we call it.
I just have to interrupt. Could you maybe explain to people what dominant means?
Okay. Excuse me. Yeah, so please interrupt me if I'm using terminology that may not be familiar to all of you. Dominant means that when you're carrying the disease and you transmit, you have a chance to transmit the disease allele to your offspring with 50% chance. So that means that all SCA patients also have an affected parent. And this is actually the thumb rule. And so every SCA patient also has an affected parent. And then for the children of the SCA patient, they each will have 50% chance to inherit the disease as well. And this is what dominant means. It is a disease that occurs not early in life. So you can have normal teens and 20s, and then maybe slowly in your 30s or even in your 40s, the first symptoms, the gait ataxia, might appear. And then often people get diagnosed. So this is a disease that occurs relatively late. For doctors, it is not very easy to distinguish between the different subtypes of spinocerebellar ataxia. We know at this moment around 48 different subtypes, and this is based on the genetic background of these subtypes. And the genetic diagnosis is often the confirmation of the clinical diagnosis. And unfortunately, despite that we know so many genetic subtypes, still in 30% of the patients with spinocerebellar ataxia, we are unable to make a genetic diagnosis. The disease is relatively slowly progressive, but of course there are exceptions. For example, patients that suffer from spinocerebellar ataxia type 3 can have a quite profound disease progression compared to the other SCA types.
And I suppose if they have additional diagnosis on top of their SCA, that may affect things.
Are you inquiring regarding are other neurological features that these SCA patients may suffer from?
If they have SCA plus something else, like maybe they have cancer or whatever, right?
Yeah, this is a very intriguing question. We do see that there may be some comorbidity with other diseases. However, the numbers of SCA patients is relatively low, that such studies have not been well executed. So we see, for example, that ataxia and gluten intolerance is something that often co-occurs, but there are many other examples out there. But for me, it's quite difficult to give a clear estimate on what the odds would be that you would have a comorbid disease with ataxia.
Right.
Yeah.
One more question on this topic. Occasionally I've run into people who have SCA, but say that they don't have any family with the SCA, right?
Yeah.
So that leads me to believe either they were misdiagnosed or they were adopted, right? What do you think about that? Can there be anybody who doesn't have a parent with SCA?
Oh, this is a difficult question to answer. I could give a multifold answer to this, and indeed, we recently know that you also can acquire diseases that are not hereditary, such as, so it is a genetic disease, but you did not inherit it from your parents. And these mutations we call de novo mutations. So sometimes somebody is born with a mutation in the DNA that is not inherited from either parent. And this mutation is acquired during the development of the embryo. So then it can indeed be that this person is the only affected individual in the family at that point. And indeed can have unaffected parents. However, often these cases have an early onset. De novo mutations often have a bit more pronounced effects on the disease outcome. And often we see that these patients have an earlier age of onset and a more pronounced disease phenotype.
Sorry, how do you spell that? Was it
de novo? De novo mutations. Yeah, this is a new class of mutations that have been identified, let's say 7 or 8 years ago. And so far, also in the field of spinocerebellar ataxia, you will find that there's not much literature on or reports that have investigated the existence of de novo mutations in patients with, let's say, the late onset spinocerebellar ataxia. Whereas we now have learned over time, and we're actually working on, we're actually involved in one of the studies in spinocerebellar ataxia type 13, but also in number 19, where we have learned that children with a very complex neurological phenotype, including cerebellar ataxia, carry all de novo mutations in the SCA disease genes that normally would lead to an adult onset spinocerebellar ataxia. So this is then the main difference between de novo mutations and the so-called heritable mutations.
right?
There's a clear difference. Yeah.
Okay. And what is the SCA landscape in the Netherlands? Like, how many people have it?
Mm-hmm.
How frequently does it occur?
Yeah, so this is at the moment, we do not have updated statistics on the prevalence of spinocerebellar ataxia in the Netherlands. The last study that was performed was back in 2005 by one of my colleagues, Professor Dr. Bart van der Warrenburg. At that time, we identified over 600 spinocerebellar ataxia patients in the Netherlands. And we, at that time, were mainly seeing patients that were affected with the so-called polyglutamine spinocerebellar ataxia subtypes. So this is a different subclass of spinocerebellar ataxias that are caused by coding repeat expansions in the respective disease genes. And these are the most prevalent in the Netherlands, and with the highest prevalence, I think it's SCA3, and then it's, I have to say this correctly, and then I think it's SCA6, and then it's SCA1. And in the years to follow, and this is also where my work comes in, is that we have identified founder mutations, and these are mutations that you can trace back to a common ancestor in a country. So in the Netherlands, we have a founder, and a very far, how do you call this? An ancestor that has spread his genetic material over the Netherlands for hundreds of years ago for spinocerebellar ataxia type 14. So we have relatively a high prevalence of this subtype in the Netherlands, but it's only because of one founder that was found to be quite successful in reproduction.
Yeah.
But for the other more recently identified spinocerebellar ataxia subtypes, we have learned that they're very rare. So they have a prevalence that is approximately of 0.5% in the ataxia population. So that's quite rare, quite rare.
Okay, and this brings up another question that I've wondered about. Is there any correlation between like environment and maybe climate in terms of the prevalence of SCA? Like, are more people with SCA typically in more winterized environments, or does it matter?
I think that's just a coincidence.
Yeah.
Spinocerebellar ataxia is by nature a genetic disease. So that's not correlated to where you live. And of course you can have these founder mutations that I've just described. So it could be, for example, coincidence that if we look, for example, so SCA3 is the most prevalent subtype worldwide, and many studies have appeared over the last years. Also on the prevalence, and we have learned that you know, we have a big founder population in South Europe, but also across the ocean. But I think, you know, people just traveled. It was a natural traveling route in the old days for trading. And I think that this is how the disease has spread, but not because of the weather. I think it really has to, you know, it's by nature, it is a pure genetic disease, and the environment can indeed modify it. So it could very well be that people that live more in southern countries, in southern Europe, and I will put it in my own perspective, that, you know, the weather could be beneficial for them because of the humidity, because of the warmth. But for others, it might actually could have a negative effect. But I think this has to do with the intrinsic characteristics of the individual, rather than that we can generalize it and say that it would work in the same direction for all ataxia patients. But yes, the environment can be a modifier of disease. This is how we would call it. And so it could change how the disease manifests and how it progresses.
Is there an ataxia network in Europe?
Definitely, yeah. We have the so-called SCA consortium, and also SCA Global has recently been initiated. And these are two, so SCA was one of the early networks that where all doctors and scientists gathered to share their ideas, to share information on patient cohorts, to lump patient cohorts, because we needed larger numbers to be able to perform our research studies. And this has led to many successful papers, and many interesting things were observed within the studies that were performed within this consortium. However, due to funding, the SCA consortium could not continue, but now a new initiative has started. This is the SCA Global initiative. And here also all the European countries contribute with their knowledge, with the patient cohorts that were already part of the SCA consortium. And they're highly active, and actually there is an online meeting upcoming in October, where all, and my team as well, we're presenting some of our latest research findings on spinocerebellar ataxia.
What is sort of the current research environment over there? Like, what is the thing you're working on, or have in view for the next few years?
That is a very good question. And so the research environment in the Netherlands is, how to say this? I think we have an excellent research environment. The university that I work, and where many other researchers work, I think they facilitate research to the highest level. And what we see is that, and this is also what the grant agencies asks us, is that we need to think about the benefits for patients. So what will it bring for the ataxia community? And one of the things, of course, that has been our main focus over the last 10 years is to identify novel disease genes for spinocerebellar ataxia. But on top of that, as I already said, that we also have the aim to understand how the disease evolves in the brain, with the ultimate goal, of course, to stop it. And for that, we need to do more fundamental research. And actually, for fundamental research, the scientific landscape is getting worse. So with that, I mean with that is that the finances are more focused on direct translational research, in the sense that it would benefit the that it would benefit the ataxia community directly, rather than gaining knowledge with fundamental research. So this is where we feel that things are changing a little bit, and that's quite, I find it also quite disappointing, because I think it is very important also, in addition to, you know, identifying these novel disease genes in order to improve genetic diagnosis for patients, and ultimately maybe give insight in what will be a proper treatment for the symptoms, I think it's also important to gain novel insight into the disease mechanisms. Because without that, we would not get any step further towards the treatment or a cure. And this is really necessary.
Many people in our community have questions around the cure and clinical trials. Can you shed some light on that?
Well, I have to confess, so that, yeah, I have to make a disclaimer that I'm not a medical doctor. And as said, I'm by nature a geneticist, a human geneticist that focuses a bit on functional genetics. And I'm not so much involved in any clinical trials at the moment that are currently being performed on spinocerebellar ataxias. However, of course, I'm aware that they are there. And one of the latest trials that we were involved in was the trehalose trial. And trehalose is a sugar agent that was administered intravenously in spinocerebellar ataxia type 3 patients to prevent the disease protein from aggregating, because actually this is the underlying problem of these coding polyglutamine repeat SCA types, is that these repeat expansions in these SCA genes and the respective proteins, that they start to accumulate in the cells, in the neurons of the brain, and these are the toxic elements. And so if you would prevent this accumulation of these toxic species in the nerve cells, you could try to either delay the disease onset or stop the disease progression. So trehalose, this sugar molecule, has such a characteristic that it would prevent the accumulation of the disease protein in the cells. And the clinical trial had some slight successes. So they noticed that patients, SCA3 patients that received trehalose, that their disease progression was less severe than patients that would receive a placebo. And the disease progression was only a few points on the SARA scale. So the SARA scale is a scale to measure the severity of ataxia symptoms. So it was not a big improvement, but at least it didn't progress further, as was seen in the patients that received a placebo. And actually, this is one of the last trials that I was aware of that also we, as the ataxia community in the Netherlands, have been involved in. But of course, many other opportunities are out there. But as far as I know, the Netherlands up to now was not involved in any of them. And that is, of course, quite disappointing also for the ataxia community in the Netherlands.
Where do you present your findings?
That's a nice question. So we typically present at scientific conferences. So here we submit summaries of our findings, and we always have the ambition to orally present at these conferences our findings to our peer community. So often there are our peers, so people that are also from the scientific community. We go to specific ataxia-oriented meetings, but sometimes we also go to the more broad and neurological meetings, so neuroscience meetings, and they could be in Europe, but sometimes we used to travel also to the United States and attend scientific conferences there. And one of the things that I also do, and this is what I also told you a bit in our pre-chat before before we went live, that I'm part of the board of the Dutch Ataxia Society, and I write sometimes summaries of our findings. We have this magazine for the Ataxia Society that's being read by all the members of this society, and so I try to keep everybody involved actually what is ongoing for the research within my team. And on the yearly contact day, we select topics from all scientists throughout the Netherlands, and we present our results there. And we recently started a 2-yearly Dutch Ataxia meeting, really to bond all the Ataxia researchers in the Netherlands. We're such a small country, but even in such a small country, sometimes it's difficult to find each other in the right manner. So we wanted to facilitate a platform where we could meet and where we could share our knowledge and we could start new collaborations. And this is highly intensified by the Dutch Ataxia Society. And this is very much appreciated. And they really take the lead in this. And it gives a great dynamics in the Ataxia community within the Netherlands. And due to COVID, this year's meeting was postponed, but we hope to have a live meeting in 2021 again. Yeah.
And is that magazine that they publish in Dutch or in English?
No, the standard way of publishing is that we do it in English. And so all the scientific papers that the Ataxia research community produces is all being written in scientific English and is submitted to peer-reviewed journals. Yeah, so this is, and of course there will sometimes be, but this is more like a clinical journal. There might be some exceptional papers being submitted to this Dutch journal, but this is actually hardly ever done. Yeah. I would say 99% of all the work that Ataxia of the scientific community in the Netherlands produces is written in English.
Do you collaborate with any research? Do you do any research collaborations with anyone in North America?
So we used to have a collaboration with Professor Harry Orr. He's in Minnesota. So we had some shared students, some master students that we exchanged. So this is actually the only collaboration that I had on Spinocerebellar ataxia, actually in the northern part of America. And I have a very close collaboration with a professor, Laura, and she is in Brazil.
What are some current challenges you face in terms of research? I know you mentioned some before, like I think funding was one.
Yeah, one thing that we encounter, and I think I'm not the only one, not the only researcher that focuses on rare diseases, is that the funding options for rare diseases is often more limited than common diseases. And we always have to, well, how do I say this in English? We always have to convince people why it is important to do research on a rare disease such as Spinocerebellar ataxia.
Yeah.
And whether or not it would be possible if we could learn something from the more common ataxias or from more common neurodegenerative diseases and then place it back into context of the more rare diseases. And this is actually, I think, the most challenging issue that we currently have, is that indeed the funding is more focused to, let's call it the more important diseases. So the ones that are very, very prevalent and that everybody knows. Because this is also, of course, a bit of the issue that we have with ataxia, is that the awareness for ataxia is not as high as it is for, let's say, cancer or any other disease, actually. And this is something that really, it's really a pity. And so any type of medium that can help to raise the awareness for ataxia is fantastic. Yeah.
How do you choose the research topics that you choose to work on?
This is based on the genetic findings that we do in the genetically undiagnosed patients. So the disease gene that we discover decides what will be my research focus for the coming, let's say, 2 to 3, 4 years. So this is why I have been moving around from research topic, in the sense that the central team was always Spinocerebellar ataxias, but I have been working on subtype number 14 for a couple of years during my PhD period, but also as a postdoctoral fellow. And then we identified the SCA23 disease gene, and this was a highly exciting gene with a very super interesting biological function. And I thought, I'm not an expert on the disease protein, so this is my thing. I'm not a hardcore biologist. I'm a simple human geneticist. So for me, I can do research up to a particular level, and then I have to make a decision whether or not it would be smart to really go in depth and do the core fundamental research on protein A, as to say. And then for me, it feels better if I would just change gears. So this new disease gene then popped up, and I thought, this is fantastic. And then we start working on that finding. And then if I'm lucky, I'm able to get some funding to hire PhD students, and then we can work on this focus project for another 4 years. And then in the meantime, we identified the SCA19 disease gene. This was a potassium channel. So then we started to work for a couple of years on potassium channels. And actually, this is how I make my decisions. And sometimes I decide not to continue on genetic findings because of the fact that the disease gene, that there's not much known about the biological function of the disease gene. And then you might say, yeah, but this is just as exciting, right? There's nothing known, so there's many things to be discovered. But it also complicates your research if you do not exactly know where to look for. So sometimes I do make decisions on what I follow up or what I will not follow up. But it's mainly the observations that drive the way that the roots of my research career over the last 10 years. Yeah. And actually what has happened, so maybe this is something to add, is that something new that came our way, actually, because we geneticists, we search in our DNA for genetic variations, and the technology has changed dramatically over the last 10 years. And now we can screen the whole genome. So we can really literally read every code of our DNA. And now we have a big problem of understanding what all the different letters in the DNA actually functionally do in our body. And we also feel that maybe some of the letters that are not part of the so-called coding part of the DNA, so the part that contributes to producing the genetic material that encodes for the proteins. So this is where we see new opportunities. So we now also start to investigate the non-coding, and so the more mysterious part of our DNA, and see whether or not we could identify some genetic variations in that mysterious part of the DNA that also could lead to disease. So this is a whole new era where we're currently moving into. And this is where I see that some of the research within my team for the coming 2-3 years will focus on.
Can people reach you if they have some questions about the SCA, and if so, where?
Yes, definitely. So again, if the question is very much clinically related, I'm not the right person to come to, and then I will refer you to my colleague, this Dr. Corien Verschuren. She's a clinical geneticist, and she's really an expert on all these types of questions. You can directly email me on my work email. I think it's d.s.verbeek@umcg.nl. You can find me easily on the web if you just type in my first name and last name. I think our UCG or our university website is clear enough. You would find me directly. Just pop me an email. I prefer that. Yeah.
And it's sorry, your name is pronounced Dineke.
Yeah, right? Dineke. Yeah.
Okay, so Thanks a lot for answering all these questions. Now I'm going to unmute everyone and they can raise their hand and ask whatever question they want.
Sure. Yeah, happy to have any questions.
Sure. So everyone is free to unmute themselves now, and you can ask any questions you have. Well, I'll go ahead and ask the first one because I know there are a few people here with SCA8.
Okay.
And I was wondering if you have done any research, and if so, are there any developments you know of in terms of SCA8?
That's an interesting question. So SCA8, yeah, this is one of the so-called non-coding. This is a very interesting subtype that is a different category that's a difficult word in English, category than the coding polyglutamin repeat expansions and all the other subtypes. It is caused by a huge repeat expansion in this mysterious part of the DNA, the non-coding part. And we know that patients exist. Even in the Netherlands, I think a few of them were diagnosed with such genetic variations at the locus that was identified to be causative for SCA8. But it is very rare. A new disease mechanism was found to underlie these types of SCA types with these alterations in the non-coding DNA. We have learned that toxic RNA fragments, so RNA is actually the inverted letter code of the DNA. That is the intermediate step towards making a protein, accumulate in cells. And I know that some studies have been initiated on different subtypes, such as SCA8, also in the United States. But I think it's quite exceptional. And I'm not the expert, actually, to confess, to really state here that I literally know all the ins and outs on the current state of the art on research in SCA8.
Do you know anyone who would know that? Or
yeah, I'm thinking. Yeah, I'm thinking on the research that actually I should know. That's of course where you want to give an appropriate answer. I'm having doubts. Laura Ranem. Laura Ranem is actually, she's one of the lead scientists when it comes about SCA8.
Do you spell her last name?
R-A-N-U-M. Laura Ranem. And I'm going to check out where actually.
Yeah, I think I found it.
Yeah?
She works at the Center of Neurogenetics.
Yeah. Question is where? Yeah, she works. Yeah, indeed. I think we're at the same.
Yeah.
Yeah. She's. I would highly recommend, if you would have specific questions on SCA8, to contact Laura.
Okay. So anyone who has a question is free to unmute themselves and ask it, or I can ask it if you prefer. Let me go back here through the chat. We had a question from Amy. Can exposure to environmental substances, chemicals, bring on symptoms?
I think indeed that the environment can be a trigger, especially also chemicals. We have learned from the Parkinson's disease research, and of course this is a completely different disease than Spinocerebellar ataxia. We have known that indeed these toxic agents in the environment can indeed be a trigger to induce disease symptoms. However, as said, Spinocerebellar ataxia is by nature a genetic disease. So to develop the disease, you need to have the genetic variation. This is the most important. Without the genetic variation, you will not develop the disease. And in this case, then the toxin that is in the environment can modify the age of onset or the disease features or the disease progression. But it will never be the trigger of the disease itself. That is really your genetic composition. It's a genetic disease. However, there are ataxias that are not genetic, that do not have a genetic background. And
acquired ataxia.
They are acquired. But this is a completely different class, a different group of ataxias. And for those, indeed, it might be, as you even have drug-induced ataxia. So people that take particular drugs, I know that some anti-epileptic drugs sometimes have, they sometimes can induce ataxic features as well. So, but these are the acquired ataxias. So this is a completely different class of ataxia.
Well, I determined that from talking to a few acquired people that basically anything that causes injury to your brain has the potential to cause ataxia or Parkinson's or some sort of neurological problem, right?
So sorry, Mark, I don't understand your question, or is it a comment?
Anything that causes a brain injury, like maybe lack of oxygen to the brain, or head injury, can cause an ataxia or a Parkinson's or something like that.
So for that, actually, I have to spare you the answer. Actually, I'm not aware of such cases, but you could foresee that if you would have, I'm going to think out loud, if you would have a tumor in your cerebellum, that could be the initiator of an ataxia. But I'm not sure if you would fall on your head, let's assume, or you would bump your head, or you would be a soccer player, or a boxer, for example, as we know with Muhammad Ali. You know, he boxed for many, many years, and indeed that led to severe neuronal loss and eventually Parkinson's disease. I'm not aware of these examples for ataxia, but maybe they are out there. But if they are quite rare.
And a question about the spinocerebellar ataxia. So basically it means spinal means it has something to do with the connection between the spine and the cerebellum.
Exactly. So now we have to talk a bit more about the brain pathology. So, but actually what we have learned from post-mortem investigations is indeed that also the spinal tract and the spinal cord and the pons is heavily involved in the pathology of spinocerebellar ataxia patients. And this is actually where the name is derived from. Yes, yeah. So it involves more than just it's more than a disease of the cerebellum. So this is really a misconception that people have. And the key feature or the key pathology that we see is indeed in the cerebellum, where we see that the cerebellum shrinks, it becomes smaller, there is loss of nerve cells. But in addition to all of that, other regions in the spinal cord and in the pons are getting affected, or even in other brain nuclei like the basal ganglia may get affected in the end, and that all contributes to the etiology of the disease.
But all ataxias have something wrong with the cerebellum, right? That's what they all have in common.
Yeah, this is what they have in common. Yeah. So actually for all of them, we clearly see this pronounced cerebellar atrophy when it comes about the late onset spinocerebellar ataxias. And so the de novo mutations in spinocerebellar ataxia genes, these children, they already born often with a small cerebellum. So then we do not talk about a degenerative phenotype. It's a developmental underlying problem rather than a loss of the cells. They're just not born and grown in the proper manner. But indeed, they all share the same pathology, this pronounced cerebellar atrophy. The loss of this are major neurons, the so-called Purkinje cells that steer our coordination and keep us upright while walking, These are severely affected in all SCA types that we know so far. So this is the common theme, and we researchers and also my team, we all have the question: how is it possible that so many genetic variations throughout the genome can all lead to a similar pathology in the cerebellum? And what does that tell us? You know, what can we learn from this? And actually, it has taught us that there are many shared disease mechanisms between the different spinocerebellar subtypes. And this really opens up opportunities to find a common intervention for multiple subtypes at once, rather than only focusing on one subtype. And this is actually the next step that we hopefully will take in the future when we have the proper model systems. And one of the things that is really that will be the future is the organ on a chip field. And our laboratory is currently setting up this technology to see if we also can get cerebellum on a chip. And that would allow us to really go more in depth in the underlying disease mechanisms and to pinpoint what these shared mechanisms are that underlie the different spinocerebellar ataxia subtypes.
And well, since nobody's asking any questions, I've got some more. I've talked to many people with SCA, and some people have a symptom called Dysarthria where their speech is slurred, but other people, they sound totally fine. Yep. So is that a question of specific subtypes may cause a speech issue, or is that a mutation specific to one person?
Yeah, this is also a very, very good question. And here again, I have to spare you very likely the correct answer, because I actually do not have the right answer, but we have learned, you know, by gathering all this information on clinical features per patient, and we try to group them per SCA type, and then we try to make so-called correlations between the SCA type and the symptoms that somebody presents with. You know, can we predict what the set of symptoms or features will be if somebody carries a genetic variation in SCA1, for example, or in SCA3? This is quite difficult, I have to confess. So indeed, sometimes a person has dysarthria where another person does not have dysarthria at all, or very mild. And actually, we do not understand this very well, but here very likely also modifiers of disease are at play. So it could either be your genetic, your other genetics, the remaining genetics that may contribute to this, or something else. But I do not have the right answer to this.
Okay,
yeah,
that's fine.
It's quite difficult to assess clear correlations. The only clear correlation that we know that exists is really the disease progression and the coding polyglutamine SCA type. So all patients that suffer from these coding polyglutamine SCA types, so SCA1, 2, 3, 6, 7, 17, they all have a faster disease progression than all the remaining SCA types. And this is the strongest correlation that we can find. And for all the other features, the correlations are quite mild.
And what was that, a glutamine?
Yeah, so these are and so we have a particular DNA code, CAG, that is being translated into the amino acid glutamine. And what these SCA types have in common, that within the protein, they have a stretch of these glutamines flanking each other. And what we have seen in the DNA of patients is that this CAG repetition is expanded. So instead of 14 glutamines, a patient can have up to 14 or 15 of such glutamines in the protein. And this elongation of this polyglutamine stretch, leads to this misfolding of the protein that I mentioned earlier. And when this protein misfolds, it cannot perform its function. And so you have a loss of function. And on top of that, also this clumping of this protein in cells is damaging to the cells. And so we all try research is focused to trying ways to prevent disaggregation. But these patients that suffer from these particular subtypes with these coding, elongated polyglutamine stretches, such as SCA3 patients, such as SCA1 patients, they on average all have a faster disease progression than all the other SCA subtypes that we know so far.
Okay, I guess I'll give one last chance to anyone who wants to ask a question. Just go ahead and raise your hand, or anybody else?
Sorry, Mark, I've had my hand raised, but that function doesn't appear to work on my system.
You know what? No, it does, but I'm blind. I didn't see it.
Sorry. Okay. Can I proceed with my question?
Go ahead.
I'm very interested in the drug-induced ataxia.
Mm-hmm.
And masquerade as another form of SCA.
Mm-hmm. It's not another form of SCA. It is it's an acquired ataxia, and somehow the drug affects the neurons in such a way that it induces the ataxic features, such as the gait disturbances and the balance manners, and sometimes also the speech may get involved. The biggest difference with these types of ataxia is that there is no loss of neurons. And so with the spinocerebellar ataxias, this is really what we call a neurodegenerative disease. So you lose your neurons over time while you age. And this is this is how the disease progresses. But with the acquired ataxias, it's rather a dysfunction of the neuron cells that are there. So at the moment that you take away the drug out of the equation, often you see that the symptoms disappear. But this is not always the case. And why that is also not very well understood. But for some patients, for drug-induced ataxia patients, the best way is just to stop taking those drugs and try to find a proper alternative, which of course is not always that easy.
But that may or may not alleviate the situation, right?
Sorry, what did you say?
That may or may not alleviate the situation.
Yeah, definitely.
Depending on the half-life of the drug.
Definitely, half-life is important, and whether or not indeed it blocked particular receptors, and indeed how fast the drug is out of your system, and whether or not indeed it has caused irreversible damage to the communication of the neurons. And this is something that is very difficult to study in humans. So for that, we need an organ on a chip. And this is actually, so I think really, it's not that I want to sell this, but I think that once we have such a model system in hands in which we can study human genetics and also the interaction with the environment, we could address those types of questions. Now it's just a bit of speculation, but it's a very, we could learn so much from it as well, if we would understand it,
And that's called organ on a chip.
Yeah, organ on a chip. Yeah.
I just looked it up. I've never heard of that before.
Yeah, this is also the EU, so the European Committee wants us to stop using animal models. So the majority of research when it comes about model systems, well, also for spinocerebellar ataxias, is mice. So people generated mouse models mimicking human disease. And of course, that had many, many pros, but also a lot of cons. And one of the cons actually was that if a drug or a therapeutic compound was identified that would stop, reverse, or halt the disease in these mice models with a particular spinocerebellar ataxia, and then they would bring it to a clinical trial, but then it would fail miserably because a mouse is simply not a human. And one way to overcome this is to generate organs on a chip that have a human origin. And for that, we need to make use of stem cells that we get either from the blood or from the urine of humans. And we can transform them back in nerve cells. And we could put them back into nerve cells of the cerebellum, for example, and then put them on a chip, and then you could pursue your studies. Yeah. This is a challenging technology. It's also an expensive technology, and not every laboratory is at the moment equipped to do these types of experiments. So it will take another 5 to 10 years before this will be this will be then generally available, I would say, to many universities all over the world. But for now, it is really specialized to a few of us that were lucky to be in the position to have the access and money to perform these types of experiments.
Okay, well, I guess thank you very much for your time. I'm sure you have some work to get back to. So,
Definitely. But it was really my pleasure. Yeah.
Okay.
And,
Have a good rest of the afternoon.
You too. And thank you all for listening and asking a few questions. I wish you all a nice day.
Okay.
Thank you very much.
Okay.
Bye.
Bye-bye.